Ever wondered what it would be like to not just use a game engine, but to actually, build your very own? One that's perfectly tailored to your unique vision, maybe even in just minutes or hours. Imagine having like a digital blueprint for your entire game's technical foundation, a complete spec written in a language that, well, both humans and advanced AI can understand, like intrinsically. It sounds a bit like the ultimate developer wish list, doesn't it? A dream where the tools finally adapt to you instead of you always bending to the tools.
Oh, absolutely. For way too long, game development has felt like this challenging dance with giants, right? These huge monolithic engines. They're incredibly powerful, sure, feature rich, definitely, but they're often pretty opaque under the hood, rigid. And honestly, just getting started can be super resource intensive. They tend to push this kind of one size fits all thing onto creators, and that often forces you to conform your really cool, innovative ideas to their way of doing things instead of empowering you to really define your own technical path. And that often leads to compromises right from the get-go. A unique vision might get watered down just to fit inside the box.
Which nobody wants, obviously. Well, today we're diving deep into a concept that really promises to flip that script entirely, to sort of redefine how we even create real-time interactive stuff. The Model Context Protocol, or MCP. Think of it maybe as infrastructure as code, but specifically for game engines. You might recognize that term from cloud computing. We're going to unpack how this open standard, especially when you combine it with smart AI agents, isn't just another tool in the box. It feels more like a fundamental shift, a real paradigm change in how games and actually all real-time simulations get conceptualized, built, and even evolved. Our mission today is really to show you how MCP enables these completely unprecedented tech and platform capabilities, how it gives you, the developer, just immense agency, flexibility, and a truly bespoke way to create. We're talking about rethinking the core tools here.
Precisely. And as we dig in, you'll discover the core ideas MCP brings to the table. Things like declarative design, absolute determinism, and dynamic evolution, all applied to engine creation. And these aren't just buzzwords, right? They represent a real transformation, taking these complex, often kind of scary technical decisions and turning them into clear, manageable, and highly auditable configurations. You'll see how MCP basically acts like a universal translator. It bridges that gap between your abstract creative idea and the actual concrete executable code. And that opens up entirely new avenues for innovation, not just in traditional games, but think about specialized simulations, cutting-edge film production, scientific visualization, so much more. This isn't just about going faster. It's fundamentally about reclaiming control, ensuring quality, and building this deeply integrated smart workflow that actually responds to what you need.
Okay, let's really unpack this challenge then. I mean, many of you listening right now are probably nodding along, right? You know the hurdles, the frustrations of building stuff today. You pick an engine, maybe Unity, maybe Unreal, and look, they're amazing pieces of tech, no doubt. Incredible out-of-the-box power. But you also find you're inheriting this just mountain of code and systems underneath, a lot of which you might not even need or want for your specific thing. It's kind of like buying a fully loaded SUV when all you really needed was like a nimble little city car. Yeah, it's powerful, but it comes with all this extra weight, complexity, systems you just don't care about.
That's a great analogy, yeah. Our sources consistently use phrases like wrestling with monolithic engines. It really captures that struggle. Just getting started can mean weeks of fiddly setup, configuration, fighting against the defaults. These engines, they're inherently developer heavy. They demand a lot of expertise, and often, yeah, they force you to bend your vision to fit their pre-built systems. You end up fighting their update cycles, dealing with these abstraction leaks, where the engine's guts suddenly spill out and you're dealing with low-level stuff you thought was hidden. Or you're constantly hitting performance ceilings. It often feels like you're working inside a black box. It really limits your creative freedom, your technical agency, because the engine ends up dictating to you, not the other way around. And that rigidity, well, it almost always leads to compromises from day one. Your really unique idea might get smoothed out just to fit the mold.
And it's crucial to remember, this isn't just a game dev problem, is it? We're talking about a huge market here. Billions of dollars, things like specialized simulations, complex scientific visualization, high-end cinematic production, architectural walkthroughs, even medical training apps. These are all industries that need high-fidelity real-time rendering, they need interactivity, but they really struggle to find platforms that are adaptable enough, that are tailor-made. They need really specialized tools and workflows that these big general-purpose engines just aren't designed for, not efficiently anyway, not off the shelf.
Absolutely. The sources are pretty stark about it. Building a modern, high-performance, real-time engine from scratch for those specialized needs, it's extraordinarily expensive, incredibly time-consuming, and notoriously error-prone. The sheer cost and complexity just mean most teams can't afford to build their own bespoke solution. And that leads straight back to those painful compromises we talked about. I mean, imagine trying to build, say, a super specific, medically certified surgical simulation using an engine primarily built for fast-paced shooters. The impedance mismatch, right? The fundamental clash between the tool and the job, the wasted resources, the technical debt just piles up. It becomes overwhelming. And that's exactly where a truly custom purpose-built approach becomes, well, not just nice to have, but an absolute necessity for these high-stakes domains.
Okay, so here's where it gets really interesting. This is where MCP starts to look like a real game changer. Cadence, the platform we're focusing on today, positions itself as nothing less than a paradigm shift in this whole space. It's not just another engine. It's an AI-native engine generation platform. The whole idea is to fundamentally return the power, the engine itself, back to the creative developer. It's all about empowering you to be the real architect of your own digital world, right down to the foundational code, the core capabilities.
Right. And the core of this solution, this shift, is what the sources call an AI native infrastructure as code engine framework. So instead of wrestling that monolithic beast, you now define your engine systems, rendering, physics, animation, scripting, networking, all of it. You define it declaratively. Using the Model Context Protocol, MCP. This isn't just about making things simpler, it's about empowerment, because this declarative approach then allows intelligent AI agents to actually generate, maintain, and dynamically evolve these systems for you. So you shift from being just a user of a static pre-built engine to being the designer of an engine that's perfectly suited, specifically tailored, and continuously optimized for your project. With AI acting as this incredible, powerful co-pilot, that's the fundamental tech shift MCP enables.
So practically speaking, what does this actually mean for you, the developer listening? How does this declarative AI-driven thing powered by MCP really change your day-to-day work, your project's future?
Well, the impact is pretty profound. Our sources explicitly mention a dramatic cut in time to prototypes. We're talking from weeks down to mere minutes or hours. Just think about the difference that makes. Going from an idea in your head to a playable, fully tailored prototype incredibly fast. That's not just a small improvement, that's a game changer for how quickly you can iterate, explore ideas, validate your core gameplay loops super early on. Plus, all those critical architecture decisions, they get captured as code, providing that infra as code for engines, which guarantees consistency, ensures reliability, and crucially gives you the power to reproduce your engine's exact configuration anytime, anywhere, on any machine.
And it creates what they call full traceability, right? Which is something I know a lot of devs and tech directors really want, but it often feels kind of elusive with traditional tools. Being able to trace every single decision, every config choice from your high-level goals all the way down to specific engine modules, the generated code, even the final build files. No more mysteries, no more fighting opaque systems or undocumented stuff. Just a crystal clear, auditable trail of how your engine was built and how it changes.
Exactly. That level of traceability is invaluable, especially for debugging, for compliance checks, for long-term maintenance, and it goes beyond just the initial generation. It establishes this continuous iteration loop with telemetry and design deltas, which means your engine isn't just a one-off static build. It becomes this living, adapting system. It can continuously evolve, refine itself based on real-time feedback, performance data, player telemetry from your actual game. It's dynamic, responsive.
The overall vision here is, well, it's incredibly compelling. An extensible modular AI-driven infrastructure where the engine itself isn't some static tool anymore, but a living part of the development experience. You don't just use an engine. You actively define it, you shape it, you assemble it exactly for your game, your needs, your audience. And all of this, as the sources say, happens at the speed of thought. It really feels like it's about reclaiming fundamental control over your whole tech stack, letting your creative vision drive the tech, not the other way around. Okay, so we keep saying MCP, Model Context Protocol. What is this thing, really, at its core? And why is it so fundamental to this whole new way of thinking? It really does sound like the secret sauce here, the core tech enabling this entire shift.
You've nailed it. At its heart, MCP is an open standard, and it basically functions as a capability bus. Now, think of a bus not like, the vehicle, but like the central communication highway in a computer system. A standard way for different parts to find each other and swap info. MCP provides exactly that. a structured, standardized way for all sorts of different things: AI models, intelligent agents, external tools to discover, negotiate, and seamlessly use engine capabilities. And capabilities here means everything: rendering functions, physics, assets, builds, telemetry streams, you name it. It's a huge leap forward because it moves way beyond what we mostly rely on now, which is often just ad hoc SDK glue. Basically, brittle custom code integrations that break all the time when things update. Instead, MCP gives you this unified, structured language and protocol for all these different systems to talk intelligently and declare what they can do. This protocol is what makes the whole ecosystem possible.
That makes immediate sense. And you used some really powerful words earlier describing its core ideas: declarative, deterministic, and explainable integration. Can you break those down just a bit more? Because those principles seem absolutely central to the whole Cadence vision and NCP's value.
Definitely. Let's unpack those. They're key. First, declarative. This means instead of writing long step-by-step imperative instructions on how to build something you know, the exact commands, the order, the memory stuff you just described, the desired state. You declare what you want the engine to be, what features it should have, what performance you're aiming for. And the system, using AI and MCP, intelligently figures out how to build it. It's sort of like telling an architect, I want a cozy 3D isometric farming game with good multiplayer, instead of having to spec out every single line of code for the renderer, every physics joint, every network packet. It shifts your focus up from the low-level how to the high-level what. Next, deterministic. This one's absolutely crucial, especially when systems get complex. It guarantees that every build is reproducible. What that means is, if you give the system the exact same MCP input, same specs, same resource definitions, it will always produce an identical engine output, like byte for byte identical. This isn't just a nice to have. It's vital for consistency across teams. For reliable debugging, you can always recreate the exact environment where a bug happened for solid QA, and for meeting strict compliance rules. You can confidently regenerate the exact same engine version, killing that infamous works on my machine problem. It allows for truly reliable testing and auditing. And finally, explainable. This is where the AI integration really shines. It means that both the AI agents and human users can easily reason over these structured MCP definitions. This makes the complex decisions the AI makes transparent and, importantly, auditable. You can understand the why behind how the engine was built because the MCP definitions themselves are designed to be human-readable and machine-understandable. The system can even spit out detailed changelogs and clear reasons for any changes it makes. No more black boxes in your engine's evolution.
Okay, this sounds like a master plan for scalability, especially for something as complex as a game engine. How does MCP actually achieve that kind of scaling, considering all the different components and project demands?
Yeah, the secret sauce there is a really clear architectural split that our sources emphasize: the separation between the control plane and the data plane. This fundamental difference is the core scalability lever. It allows for huge flexibility and efficiency. The control plane, that's where MCP lives. It's the intelligent orchestration layer. It handles the intent capability mapping. Basically, it defines what should happen. This covers everything from engine design and config, orchestrating complex builds, managing deployments, overseeing live ops, even running fancy experimentation frameworks. MCP clients, which could be your IDE, a command line, or one of those AI agents, talk to MCP servers, which are the specialized capability providers. The data plane, on the other hand, that's the actual high-performance runtime where your engine does its work. This is how it happens. It's made up of the core engine bits. The optimized C++ or Rust ECS, the various renderers, OpenGL, Vulkan, WebGPU, etc., the physics engines, networking stacks, asset CDNs, the real-time metric streams. This is the part doing the heavy lifting, running your game or sim super efficiently.
So this clean separation, these distinct roles for the control and data planes, that's really the key to scaling the whole thing. It sounds like it lets you swap parts out without re-engineering everything every time.
Precisely. This architecture lets you change or scale the data plane behind a stable typed MCP surface. What that means practically is you could, for example, swap out your entire physics solver, maybe go from Havoc to Bullet, or adopt a different renderer API, like moving from OpenGL to Vulkan for better performance. And you can do that without having to completely retool or rebuild your whole development pipeline. The control plane, governed by MCP, stays consistent in its high-level definition of what. It just translates that intent to the new data plane components. This modularity means different parts of your engine can be developed, optimized, scaled independently. It makes the whole system way more robust, adaptable, and efficient, whether you're a small indie or a massive studio.
Okay, so MCP gives us this powerful, scalable framework. Now, what are the key concepts, the sort of fundamental building blocks we need to grasp to really speak this new language of engine generation? These sound like the things developers will actually interact with.
Absolutely. Think of these as the basic vocabulary of MCP. First up, resources. These are essentially type surfaces for things like engine specs, individual assets, shaders, materials, scene graphs, even performance reports. Imagine them as unique, addressable digital things, each with a specific type and a stable ID. This design enables some really powerful stuff. Content-addressed caching, meaning resources are identified by their actual content, which allows for massive reuse. Delta diffing, so you only track the changes between versions efficiently. And crucially, reproducible builds, because every resource is uniquely and consistently identified. For instance, a specific shader might have an ID like Cadence.renderer shaders moduli save hash. That spear of hash is a cryptographic hash of the compiled shader code itself. It's uniquely ID'd by its content. If the hash doesn't change, the resource is the same no matter where it is. Next, we have tools. These are safe declarative commands that the MCP servers expose. They provide specific, well-defined functions. Think things like build engine, validate determinism, vacant of mesh, or compile shaders. The way these are designed allows for what's called horizontal sharding, which is just a fancy way of saying you can break up huge, complex tasks, like compiling hundreds of shaders or building an engine for multiple platforms, and easily spread that work across many different computers. This turns potentially hours of local work into maybe minutes or seconds across a distributed build farm or shader farm in the cloud, all managed seamlessly behind that single MCP protocol interface.
This prompts idea sounds super intuitive, especially in this AI native context, like something I'd use to kick off an AI, or maybe complex preset workflow.
Exactly right. Prompts are effectively reusable workflows. They wrap up complex sequences of actions and configurations into a simple high-level command. An example might be, generate voxel engine with Lua scripting, web GPU rendering, and a headless server build. They're really excellent for policy-compliant scaffolding and repeatable pipelines. You define the high-level goal, and the system, through this prompt, orchestrates all the necessary MCP calls to make it happen, ensuring consistency and sticking to predefined best practices or architectural styles. Then there's sampling. This is really important for integrating large language models, LLMs, responsibly. It lets MCP servers ask a client-controlled LLM when you control to synthesize code or configurations, maybe suggest auto-refactors for your code or generate initial gameplay templates. But, and this is vital always with explicit user approval, this design keeps sensitive API keys and LLM usage under your governance, the client's direct control. It ensures security and accountability. It's about AI assisting you, not running wild, making critical decisions unsupervised. Roots define sandbox project or workspace boundaries. This is a fundamental security and isolation thing. It makes sure that MCP servers working for you can only access and change stuff within your explicitly defined project root. Prevents unauthorized access or accidentally messing up other projects, even on the same system. It's essential for secure multi-tenancy, having multiple users securely on one system, and for compliant CI/CD pipelines. Clear boundaries for everything. And finally, elicitation. This provides structured JSON schema prompts to dynamically ask for any missing configuration info that might be needed during a build or deployment. For example, you might get prompted, provide a read-only token for your artifact registry, along with a clear JSON schema showing exactly what format the input needs to be. This is an elegant way to avoid brittle bespoke UIs, those custom interfaces that are hard to maintain and always seem to break. It standardizes how missing info is requested and received, making it consistent and machine-readable without developers having to deal with complex custom forms for every little parameter.
Okay, this is where it gets really practical. How does MCP, with all these building blocks, actually automate creating a playable game prototype, like straight from an idea? This sounds almost like magic, turning a high-level vision into something you could actually run really fast.
It does feel a bit magical, but it's very carefully engineered intelligence, really. The auto game creator and engine orchestrator, that's its job. It's designed specifically to automate the first mile of game development, really. And that first mile is arguably the toughest, most time-consuming part for any project. So you, the developer, you describe your intended player experience, you talk about the feelings, the pacing, the core fantasy, you list key mechanics, themes, genre, target platforms, any constraints you have. The system takes all that high-level creative input and, using MCP, generates a complete, detailed technology plan. This whole process just collapses that initial setup phase, which often takes weeks, into a much, much shorter time frame. It really speeds up iteration.
Okay, let's walk through this pipeline then, step by step. It sounds incredible. It all kicks off with that initial creative spark, that idea, right?
Exactly. It starts with a design brief intake. That's where your initial ideas, your inspirations get captured. Could be natural language, could be structured prompts. This raw input then flows through an experience ontology plus constraints layer. Here, the system uses its deep understanding of game design to analyze the feelings you want, identify the core mechanics, understand the limitations you set. This sort of contextualized understanding then feeds into a tech requirements synthesizer. And this is what translates those abstract goals and constraints into concrete, actionable technical specs for the engine. From there, it moves to the engine configurator, MCP. This is where the system picks the best core architecture and pulls together the right engine modules. That's followed by detailed module selection and wiring to connect everything up precisely, which ultimately creates a comprehensive engine blueprint. This blueprint, which is an MCP resource itself, then feeds straight into a skeleton game generator. This scaffolds that initial playable prototype, which in turn informs a build system generator, crafting the specific build pipeline needed. And finally, it goes to a packaging and deployment MCP for handling multi-platform builds, for Steam, app stores, desktop builds. And crucially, there's a telemetry plus feedback MCP closing the loop. It captures vital data and design deltas changes that feed back into the tech requirement synthesizer for continuous, smart improvement. It's a truly cyclical, self-optimizing loop.
That initial design brief intake sounds like where the real creative magic starts getting formalized. How does the game design MCP specifically help shape that raw idea into something structured, something the engine can actually work with?
Yeah, the game design MCP is built to generate structured design concepts from idea seeds plus various modifiers. And a seed can be super flexible, could be anything. A newspaper article you found interesting, a random word, a personal story, even a detailed AI prompt. That flexibility allows for really diverse starting points. The key is that the MCP then takes this raw, often messy input and systematically gives it structure, makes it coherent and actionable.
The flexibility is brilliant. Can you give us a concrete example from the sources? Show us how a simple idea can kind of blossom into a detailed, machine-readable design concept through this.
Absolutely. Let's grab a design seed input from the material. Imagine something like this. Source. Newspaper article content. Rising sea levels threaten coastal city. Genre modifier. Roguelike. Random twist. 1920s noir setting. Feel hints. Tense. Mysterious. Urgent. Mechanic hints. Resource management. Rescue. Evacuation. Okay, so the game design MCP then parses the seed, it pulls out themes like disaster, survival, then it applies genre modifiers, deriving mechanics. It really is. The output is this comprehensive design concept resource. Let's call it Noir Rising. It would include a clear core loop, maybe scavenge rescue, upgrade safe houses if I have nightly floods. It lays out clear mechanics, specific experience goals, a cohesive aesthetic. This structured concept then emits a standardized design brief resource, perfectly formatted and ready for the rest of the engine generation pipeline to consume. It's basically a complete machine-readable design doc derived straight from your initial prompt, all managed by MCP.
And crucially, you still have full traceability, even at this early conceptual stage, right?
Exactly right. Every single design concept the GDMCP generates links directly back to its original seed and all the modifiers that were applied. That gives you complete, transparent traceability. You can always see why certain design choices were made, linking them right back to your initial creative spark. Provides real clarity from the start.
Okay, so we've got this cool structured design concept, but how does the system make that huge leap from, abstract human feelings like cozy or tense into actual concrete technical specs for an engine?
Yeah.
That seems like one of the trickiest translations in the whole game dev process, bridging that creative to engineering gap.
Yeah, this is really where the system's intelligence and the structured nature of MCP really come into their own. There's a sophisticated mapping engine inside the system. Its job is specifically to translate feelings, genre, and mechanics into specific rendering, physics, AI, audio, and UX requirements. It does this using this elaborate rule and constraint system that has a deep, learned understanding of how different design elements should map to technical choices. Let's look at some practical examples of how that derivation works. Say your experience audio goal specifies cozy. The system might translate that into concrete audio parameters. Dynamic reverb low, warm, ambient pads, subtle diegetic UI cues. If your experience rendering combines cozy plus 3D plus isometric, it intelligently implies settings like soft shadows, maybe optional SSAO, TAA off, which is important for platforms like Steam Deck to avoid blur and a stylized tone mapping profile. For mechanic systems, if you have farming plus crafting, that directly requires specific engine systems, inventory management, grid terrain tools, a time system, serialization for saving the game state. And of course, critical platform budgets are always factored in. For a Steam Deck target, it automatically implies that 16.6 meters frame time target for 60 fps, maybe half-resolution SSAO, ALO-D policy level 2, meaning aggressive detail reduction at distance, and a strict texture budget 1.5 GB to keep things running smoothly. The system meticulously figures out all these technical details based on your high-level creative intent, all expressed through the structured language of MCP.
Right, this is where the engine really starts taking shape. Once you have those precise technical requirements, how does the engine configurator MCP actually decide on the core architecture style and then assemble the specific modules from that big capability list you mentioned?
This is exactly the engine configurator MCP's job. It chooses the optimal architecture style and then expertly composes engine modules via the Game Engine Framework Factory. It uses these smart selection heuristics to decide between different architectural approaches, maybe a pure entity component system, ECS, a more traditional component-based style, or even a hybrid approach. Often the system defaults to ECS, and for good reasons, as our sources point out. It's great for large entity counts, frequent iteration, it's net replication friendly, and offers solid cross-platform performance. ECS, with its data-oriented design, just fits really well with modern parallel game development. Okay, so once the architectural backbone is set, the configurator starts composing capabilities from this huge library of specialized providers for each engine part. This covers rendering, with choices like OpenGL for compatibility, Vulkan Direct 3D for performance, WebGPU for web, physics, like Box2D for 2D, Bullet for complex 3D, audio, OpenAL, FMOD, animation, maybe Blend Tree Core for complex characters, various scripting languages, Lua, Python, C#, networking like Init UBP or Steam networking sockets, input systems, SDL2, GLFW, and flexible asset loading systems, ASIMP, custom cookers. It essentially acts like a super smart procurement officer, picking the absolute best fit components based on those synthesized technical requirements, all managed and orchestrated via MCP.
And the final output of all that complex assembly is what you call an engine blueprint, which is basically HCL-like infra-ASC code. So this blueprint declaratively defines the engine's core, its platform targets, specific rendering features like, say, Postrex and Bloom-Low, Filmic for visual style, the physics choice, the animation system, and way more. It's a complete machine-readable declarative definition of your custom engine ready for the next step. So we've got this incredibly detailed engine blueprint, a full spec for our custom engine. What happens next to get something we can actually run and play with, even if it's basic? How do we go from that purely declarative definition to an actual build?
Right, that's where the skeleton game generator comes in. Its role is to produce a runnable prototype with stubs. Now, this isn't a fully finished game, obviously. It's more like a bare-bones, functional version that gives you the absolute minimum you need to be playable and testable. It automatically includes core ECS components like transform, sprite model for visuals, physics body for interactions, inventory for basic item tracking, interactable for simple object use, and network replicated for multiplayer basics. It gives you those fundamental pieces to start building on right away. And it's not just components, it also intelligently scaffolds the essential systems that bring the engine to life. So a render system, a physics system, a time system for the game clock, an inventory system, a NetSync system, and a save load system. Crucially, it also generates basic scene structures like a loading screen, a simple test map, maybe a farming patch to demonstrate resource stuff, and a basic day-night loop to show environmental changes. Plus, it generates scripting hooks for languages like Lua and a very basic UI. This whole step transforms your declarative engine definition into a living, playable, though minimal, experience, all in a tiny fraction of the time it would normally take. It's a powerful demo of MCP driving real results from high-level intent.
Right, because a game isn't just an engine, is it? It's a world. It's filled with art, sound, interactive things, characters. How does MCP handle that massive task of managing assets, sourcing them, integrating them, making sure they actually fit the game's design and get woven in seamlessly? This feels like a huge bottleneck in most workflows.
Oh, it absolutely is. And this is where the Asset Registry Mapper MCP becomes so vital. It's the crucial bridge here. Its main job is to bridge gameplay intent to concrete asset needs. It translates those high-level game feel genre mechanics into specific, detailed asset requirements. And that covers everything: 3D models, textures, sounds, level layouts, UI elements, visual effects. The goal is to make sure every single asset, whether it's pre-made or newly generated, perfectly fits and fulfills the game's design goals and visual style. The process itself is pretty smart. First, it queries pre-built asset libraries, checks if you already have suitable assets in your collection. But if certain assets are missing or just not right, it dynamically generates asset request definitions, or ARDs. These ARDs then get intelligently delegated to specialized AI asset generation MCPs or procedural generation MCPs. Once the assets are sourced or created, whether they were pre-built, AI generated, or procedurally made, they all get stored in the central asset registry, and they're meticulously linked with rich metadata. We're talking source, the exact prompt used, generation configs, license info, version history. This deep linking ensures both complete traceability and maximum reuse across different projects.
Can you give us a concrete example, maybe for that Whisper Grove game idea? Show us how that mapping works. How does it know what assets farming needs?
Sure thing. Let's take Whisper Grove. If your mechanic spec includes farming, the Asset Registry Mapper MCP would intelligently map that to a list of needed assets. Maybe a HOTOOL model for the player, various crop models, wheat, carrots, whatever, showing different growth stages, maybe a tilled soil texture. If the design also had crafting, it might request an anvil model and a set of Recipicons. Now, if these specific assets aren't found in the pre-built libraries, the system would then generate those detailed ARDs. They'd describe exactly what's needed, the style, the resolution, everything ready for AI or procedural generation to take over. And crucially, as these assets get identified or created, the system builds an asset graph. This isn't just a flat list, it's a dynamic graph showing all the assets, any prefabs they're part of, and all their dependencies. This is vital because it lets the skeleton game generator instantiate them correctly in the game world, make sure all the pieces are there, linked up right, and perform well when the game builds. It gives you that whole picture of your content's connections.
So if you need, say, a dense forest environment or maybe a complex cave system, the systems can just make one. That feels like next-level stuff, moving beyond placing every single tree or rock by hand.
Yes, that's exactly the power of the procedural generation MCP. It provides deterministic and highly reusable asset pipelines for generating complex content on demand. This includes things like level generation, terrains, dungeons, cities, forests, model generation, think parametric weapons, varied foliage, and texture generation, noise-based patterns, stylized surfaces. This means really complex environments and props tailored to your specs can be generated dynamically based on rules and parameters you set. And each generator used in this process gets meticulously stored in an algorithm registry. This registry holds the original prompt, the full config, the underlying algorithm, and exactly how its output maps to the asset registry. The huge benefit here is determinism. You can regenerate the exact same terrain or modular prop, pixel for pixel, vertex for vertex, anytime you need to, just by reusing the original seed and parameters. For example, a terrain patch 01 might be generated by a Perlin height map algorithm with specific octaves and scale values, plus a particular random seed. This ensures consistency, reproducibility, and makes debugging procedural content way easier.
And for the assets that aren't procedural, the unique art pieces, character models, how does AI fit in there? How does it become a real creative co-pilot for making assets?
Right, that's where the AI asset generation MCPs step up. These are specialized MCPs that take those asset request definitions, ARDs, from the mapper, and they then intelligently generate 3D models, materials, textures, sounds, animations, visual effects, VFX, and UI elements. These are the powerful tools that turn your text descriptions, style guides, or reference images into actual game-ready assets that plug right into your project. And to keep things transparent and high quality, these AI generators return comprehensive asset generation receipts. These receipts include crucial info, the artifact URIs, unique IDs for the assets, full provenance, detailing the prompt, seed, generator version, and even quality metrics plus compliance checks. The asset mapper then does a rigorous validation pass, applies optimizations like generating LODs, optimizing UVs, adding collision, and finally registers the optimized asset in the central registry. This deep integration makes sure AI-generated assets meet all the technical and quality bars and are fully traceable back to how they were made.
Okay, this whole asset system, blending pre-built procedural and AI gen through MCP, sounds incredibly powerful, transformative even. What are the big practical takeaways for the developer listening? How does this change their asset workflow?
The benefits for you, the developer, are really substantial. They hit some of the biggest pain points in asset creation. First, you get unparalleled consistency. Your experience, goals, and chosen aesthetics are directly matched by the assets and mechanics. No more clashing art styles or assets that feel off because they came from different places. Second, determinism. This is huge. Procedural assets are completely reproducible via their stored algorithm and seed. Guarantees reliable iteration and debugging. You can always recreate the exact same generated content. Third, massive reuse and scalability. All assets are linked to rich metadata, making them inherently reusable across different projects in your studio. And that hybrid sourcing pre-built plus AI gen plus procedural offers incredible scalability. You can populate vast worlds or generate endless variations super quickly without tons of manual work. And finally, and this is critical for complex projects, complete traceability. Every single asset is mapped directly to its gameplay spec and its generation method. This ensures a clear, auditable history for all your content, from the initial idea and prompt right down to the final optimized asset in the build.
Okay, it's one thing to build an engine and generate assets quickly, but nowadays, building inclusive experiences is just so important. How does MCP handle accessibility? Does it help ensure games are designed for everyone right from the start, not just as an afterthought?
Yeah, that's a critical area, and it's addressed by a specialized MCP called the Accessibility and Disability Aware Fun First MCP. Its whole philosophy is to design for disability from the start, not just ticking boxes on a compliance checklist at the end, but actively optimizing for fun, agency, and flow. The vision is genuinely fun-first accessibility. It means starting by thinking about joy loops that naturally work for different bodies and minds across diverse players. The goal is to create experiences that are inherently engaging for more people. And it's guided by some core principles. Choice of play, meaning offering multiple equivalent ways to play, visual, audio, haptic, text, turn-based, to achieve the same fun and progress. No one-way door, meaning any critical interaction or puzzle must have at least one alternative path, so no one gets stuck due to an accessibility barrier. And co-play support, designing for caregiver modes or shared controls, encouraging shared experiences.
Wow. What kinds of disabilities does this approach cover? It sounds incredibly comprehensive.
It really is. The disability design map within this MCP is extensive. It covers motor disabilities, things like limited fine motor skills, one-handed play, switch access, chronic fatigue needs, vision impairments, blindness, low vision, color deficiency, photosensitivity, hearing impairments, deaf, hard of hearing, audio processing differences, cognitive and neurodivergence challenges with attention, memory, sequencing, sensory overload, speech impairments for nonverbal users, and chronic pain and fatigue focusing on pacing and session length flexibility. Each of these maps directly to specific design affordances, like bigger hitboxes, preferred input-output modes, and crucial comfort and safety policies. It's a really holistic approach. So you provide an accessibility brief as input. Could be quite specific, like disability focus, motor own-handed, low vision, ADHD, and maybe session minutes, 20 breaks allowed. True for fatigue. The MCP processes this brief through smart steps like fun loop selection and path redundancy analysis. It then spits out a detailed accessibility plan. This plan recommends things like interaction modes, maybe mod turn-based for slower pace, input options, one-handed layout, switch access, output options, UI scaling, high contrast modes, text-to-speech, and various assist features, time dilation, aim assist, puzzle hints. Crucially, it also generates a design brief patch and an input-output map with specific engine hooks. This directly influences the game's core design and implementation, ensuring these features are deeply baked in, not just slapped on top.
So it's not just theory. There are concrete design patterns that can be directly applied and configured in the game.
Exactly. There's a patterns library integrated into this MCP offering tons of concrete solutions. For motor issues, maybe generous hitboxes or remappable controls. For vision, scalable UI, audio beacons for navigation, object outlines. For hearing, full captions, haptic cues for important sounds. For cognitive or neurodivergent players, patterns like clear goals, optional guided modes, reduce sensory clutter. The end goal is to emit selectable profiles at game launch, so players can easily pick, say, a low vision or one-handed profile, and instantly get a whole suite of relevant accessibility features configured for them.
Monetization. That can be a really tricky subject, right? Sometimes feels like it clashes with the player experience. How does MCP make sure monetization is integrated thoughtfully, ethically, and in a way that actually complements the game design?
Right. This is handled by the Monetization MCP, or MMCP. It designs and operates monetization as code. This approach means monetization mechanics are inherently consistent with the player experience goals and core game mechanics, instead of being some tacked-on layer that feels disruptive. By defining it as code, it becomes transparent, auditable, modifiable, just like any other engine system. The MMCP intelligently generates a monetization plan that's aligned with the game's genre and audience. It materializes precise economy specs, detailing virtual currencies, how players earn them, sources, how they spend them, sinks. It creates IAP catalogs and offers schedules. Critically, it builds in strict guardrails to enforce ethics and compliance. Things like odds disclosure for loot boxes, robust age gates, adherence to regional restrictions, configurable spending limits. The monetization brief input even lets you specify things like no pay to win, true or no loot boxes, false, maybe with regional exceptions. It makes ethical design a core configurable part of the system.
So it actively connects with the game design and balance side of things to ensure it doesn't create bad vibes or pay-to-win scenarios.
Absolutely, that integration is key. The MMCP proposes monetization-aware content slots directly to the game design MCP, making sure any monetized items feel naturally integrated. It requests appropriate cosmetic assets from the asset registry mapper. And crucially, it validates economy pacing with the balance MCP. This last step is vital. It ensures a healthy fun versus friction balance, avoids overgrind where players feel forced to pay to skip tedious parts. Comprehensive guardrails are there to actively prevent negative retention players quitting due to annoying monetization or any pay-to-win leakage. It ensures monetization genuinely complements rather than detracts from the core experience.
Okay, in a world moving super fast, game ideas can get stale quick. Trends blow up and disappear in days sometimes. Can MCP help creators actually capture those fleeting trends and quickly turn them into playable prototypes? Let them jump on new cultural moments.
That's exactly what the JIT Trends and What's Hot MCP is designed for: extreme agility. This MCP continuously ingests fast-moving cultural trends from all sorts of places, real-time data from TikTok, YouTube, search charts. It then intelligently prioritizes them by velocity, xFit, x feasibility. How fast is it rising? Does it fit a game genre? Is it actually feasible to build something around it quickly? It localizes content for different regions and then emits monetization-aware design seeds for ultra-fast time-to-market micro-prototypes. This lets devs tap into the current zeitgeist with incredible speed. To do this, it calculates a sophisticated trend score. This score combines factors like trend velocity, its half-life, how long it might last, format fit, audience fit, content safety, all balanced against production cost risk. This scoring helps pick the most promising trends for rapid prototyping.
And this leads to incredibly fast prototyping, letting creators really seize those moments.
Yes, the goal is an L0 micro prototype, very basic, functional within an amazing 24 to 72 hours. This micro prototype focuses on a single core loop, minimal UI, often targeting a web PC build for instant sharing to get feedback immediately. The strategy emphasizes registry-first assets, using existing assets whenever possible, and only using AI PCG if absolutely needed to hit those crazy tight deadlines. The output is a trend seed plan, including the design seed, a design brief patch to maybe adapt an existing concept, a tailored monetization plan, and clear express TTM, express time-to-market targets. Streamlines the whole rapid dev process.
Okay, this next one sounds almost like sci-fi games that span the physical and digital worlds,
Yeah.
blending realities. This digital idea is fascinating.
It's a really exciting frontier, yeah. And the cross-domain Phygital Game Design MCP is built exactly for this. It designs and operates blended games combining real-world activities like walking, scanning QR codes, crafting physical things, meeting people, exploring locations with rich digital play on mobile, PC, console, VR. A single design brief from this MCP spits out both physical activity kits and the corresponding digital scenes or loops, provides a cohesive design across both realities. And some crucial principles underpin this. Safety first is paramount. Think geofences, time of day rules, crowd density caps, robust consent mechanisms for location or camera use. Also, offline capable design ensures graceful degradation if you lose signal. The experience stays functional and fun even without constant connection, which is vital for real-world play.
And it generates something called a quest graph. That sounds like a structured narrative for these blended experiences.
Exactly. You input a cross-domain brief, maybe something like City Critter Safari for 10-year-olds involving walk, skanker, photo prompt activities. You also give it a venue spec with geofences for a park or city area. This leads to a quest graph being generated. It's a detailed sequential map of both physical and digital actions. Like, maybe it tells the player, navigate to this spot in the park, scan this QR code, which then spawns an AR creature on your phone, followed by a digital photo challenge. So the MCP outputs this quest graph. a real-world artifact pack, QR markers, printable maps, maybe craft instructions, and a digital build plan for mobile web clients with AR and offline support. Privacy and ethics are baked in. Location data is coarse, not super precise. Faces get auto-blurred in photos. Strict consent rules are enforced. Ensures player safety and privacy in these blended realities.
Beyond just fun, can MCP even design effective educational or therapeutic experiences, make learning engaging and adaptive?
Absolutely. The gamification MCP is specifically designed to seamlessly integrate learning goals, specific skills, standards, outcomes, with game design principles to generate playable, adaptive learning experiences. It transforms curriculum specs into engaging quests, levels, mechanics, assessments, and personalized feedback loops. This whole robust learning plan then plugs straight into the auto game creator pipeline to generate the actual interactive learning game. What's really powerful is its ability to include personalized JIT context, just-in-time personalization. It can pull data from class rosters, student profiles, interests, motivations, accessibility needs, accommodations, even current events to dynamically patch the design brief. Makes learning hyper-relevant. There's even an opt-in therapeutic mode for clinician-supervised use in medical contexts, operating under strict safety, privacy, and consent guardrails. For example, an algebra task could get intelligently reskinned as an Aurora-themed puzzle based on a student's interest in space and a current event, making it way more engaging.
Wow. Okay, all these features sound amazing, creating complex, dynamic games. But what about making sure the game's actually fun and fair? How does MCP handle game balance to ensure an optimal experience?
Right, that's the critical job of the Balance MCP. It goes beyond just intuition using rigorous data-driven methods. This MCP runs sophisticated AI and agent playtests plus Monte Carlo simulations to really evaluate key metrics: win rates, churn points where players quit, time to kill in combat, resource scarcity, or abundance in the economy. It uses these objective insights to understand how the game really plays. Based on that analysis, it then intelligently produces diff patches against the game's balance spec. That's the declarative definition of your desired balance. These patches come with clear justifications for the changes and built-in guardrails to stop unintended side effects. For instance, if the system finds early game deaths cluster at 3 to 5 minutes due to oxygen starvation in our NOR rising example, it might propose changing oxygen.decay per sec from 0.8 down to 0.65. And that proposal would come with a guardrail ensuring the value stays within a safe, predefined range. This tuning process continuously integrates with the telemetry MCP, creating this persistent loop for ongoing data-driven optimization, ensuring your game's balance evolves for the best possible player experience.
Okay, this whole system, powered by MCP, sounds like a completely new ecosystem for making games. But what if a studio still wants to use, say, Unreal or Unity for parts of their workflow, maybe for final polish, or they have teams who are experts in those tools? Can you bridge this new AI-native world with the existing engines?
That's a really crucial point, yeah. And it's a core part of the strategy for flexibility and adoption. We get that studios have existing pipelines, existing expertise. That's exactly why external engine integrator MCPs exist. These are specialized MCPs designed specifically to export generated prototypes into popular external engines for further iteration. So no, you're absolutely not locked into just one ecosystem. You can get the best of both worlds. Rapid generation with Cadence and MCP, then finish up in your preferred traditional engine if you want. These integrator MCPs do a pretty complex but essential translation job. They take the engine blueprint and all the associated assets generated by our system and convert them into the target project format for the engine you choose. This gives you ready-to-open projects, a .project for Unreal, a .unity project for Unity, or .tscn.godot for Godot. They expertly map the ECS or component systems developed via MCP to the target engine's equivalent patterns. They package up all the registry assets into native import pipelines, handles all that complex translation automatically.
That's incredibly powerful. It means developer familiarity for teams skilled in those engines, direct ecosystem access to the huge plugin and asset stores in those environments, and a smooth onboarding for existing teams. Really offers the best of both worlds, MCP speed and flexibility up front, plus mature tools later on.
And we're aiming to take it even further. A key planned feature is round-trip iteration. This means that engine-side edits, changes you make directly inside Unreal or Unity, can actually produce change sets, JSON diffs. The integrator MCP can then re-ingest these changes. This allows the central asset registry and the core design and balance specs, all defined in MCP, to be updated. Any conflicts that pop up are intelligently handled via three-way merge. So it creates this continuous two-way flow. Changes made in traditional engines can still feed back and update the core MCP definitions, keeping a single source of truth.
What about the other way around? Say a team has an existing project, maybe already built in Unity or Unreal, and they want to bring that into the MCP ecosystem to use all these cool generative and iterative features.
Equally important for adoption, yeah. And that's handled by the Reverse Integrator MCP. This lets teams import an existing project from Unreal, Unity, or Godot and normalize it into a canonical bundle our platform understands. We call this a canonical project, CPJ. This CPJ is basically a standardized, engine-neutral representation of your entire project, makes it fully accessible and workable within the MCP framework. The import process itself is pretty comprehensive. It involves project detection, figuring out the source engine, thorough asset ingest, converting models to an intermediate format like GLTF, precise scene graph parsing, sophisticated behavior extraction, translating logic from blueprints, C#, GDScript into something MCP gets, analyzing physics and navigation, input maps, audio, and even trying to infer design artifacts like a design seed from existing tags or asset names in the old project. It systematically tries to capture the whole essence of your legacy project.
So if I'm getting this right, you could theoretically import an old Unity project, convert it to CPJ, and then maybe re-emit it as a brand new Unreal project.
Yeah.
Or even Godot. That's incredible cross-engine capability, like a universal translator for game projects.
Exactly. That's the incredible power of cross-emission that CPJ enables. Once your legacy project is in that normalized CPJ format, it can then be fed to the Generate Engine project, Integrator MCP, to produce a new Unreal Unity Godot project. Effectively changing its native engine or creating parallel versions opens up amazing possibilities for porting and leveraging different engine strengths. And critically, throughout this whole process, the system meticulously preserves all provenance file hashes, original guides, original paths, the source engine version, plus all the licenses. Ensures legal compliance and complete history, even for imported projects.
Okay, so this isn't just about making one engine or one prototype. It's about setting up a living, evolving system. How does MCP enable that continuous automated lifecycle for prototypes, letting ideas get constantly tested, refined, improved?
This is really the ultimate expression of MCP's power. An end-to-end loop that autonomously generates prototype ideas, builds and deploys them rapidly for playtesting, captures comprehensive feedback and telemetry, and then intelligently promotes the best performers to higher fidelity tiers for iterative refinement. It's like a self-improving factory for game creation. It starts with the Auto Idea Generation MCP. This agent mines tags and styles from the asset registry, seeing what content is available, and uses template combinators, smart mixing of genre, mechanics, feel, asset packs, to generate a diverse pool of candidate design seeds. Each seed gets scored for novelty versus feasibility, balancing innovation with practicality. These generated prototypes then get rapidly built using the MCP pipeline and deployed to various playtest services, maybe a private Steam playtest, a public web build, internal testing. The feedback and telemetry MCP then diligently captures a ton of metrics. Session length, specific fail points, player sentiment, surveys, feedback, detailed event traces, all crucial data for evaluation. Next, the scoring and ranking MCP applies a multi-objective score. Could be a weighted formula like W1 retention plus W2 time to retention plus W3 satisfaction plus W4 performance budget. It also uses advanced techniques like bandits and experiments, think smart A/B testing to scientifically test different ideas and mechanics. This MCP acts as a gatekeeper, rejecting ideas that miss predefined baselines and promoting the top K most promising ideas to the next stage.
And what happens when an idea gets promoted? When it shows real promise? How does it climb this quality ladder you mentioned, becoming more polished?
Right. When an idea gets promoted, it moves up a defined quality ladder, progressing through distinct fidelity tiers. Typically looks something like L gray box prototype, basic shapes. L1 stylized proxies, basic style with placeholders. L2 art complete, fully realized art, polished visuals. L3 advanced polish, final refinement, optimization, bug fixing. The promotion rules are explicitly defined by the MCP. For example, if a prototype hits D1 retention 25% and maintains average FPS U55 on Steam Deck, it might automatically trigger actions like request higher fidelity assets from AI, PCG, or artists, enable expanded render features, or tighten game balance. This continuous, data-driven progression ensures only the best ideas get further investment and are refined towards release, all orchestrated by these intelligent agents using MCP.
So this whole complex process, generation, iteration, evolution, it's not just happening on its own. It's being orchestrated by these intelligent agents. Can you tell us a bit more about these AI agents and their specific jobs in this system?
They sound like the real architects here.
You're right. The AI agent suite is really the heart of this whole intelligent ecosystem. The builder agent is basically the primary generator. It interprets structured prompts or natural language commands into specific system goals. Then it intelligently composes valid MCP configurations by picking and wiring up the right modules and resources. And finally, it calls the necessary code generation and build toolchains to actually bring the engine to life. A prompt like build a multiplayer FPS with Lua scripting and web GPU targeting desktop and web. That's what the builder agent handles. Then you have the overseer agent. This one is the maintainer and optimizer. This agent autonomously maintains, optimizes, stabilizes, and evolves the generated engine frameworks. It does crucial stuff like validating deterministic properties to ensure reproducibility, refactoring MCP definitions for clarity and efficiency, and optimizing performance parameters based on telemetry data. It's also a dedicated determinism verifier, constantly hashing and comparing builds from the same MCP input to guarantee reproducibility and flag any issues immediately. Think of it as your always-on vigilant tech director. The researcher agent acts as the knowledge scout. This agent is continuously integrating new research and advancements from fields like graphics, geometry, computing. It scours academic papers, places like Arcliffe, open source projects on GitHub, feeding cutting-edge info and proven techniques back into the system. Ensures the platform stays right at the forefront of tech.
And this spearhead agent, that sounds like the visionary of the bunch, really pushing the boundaries of what's possible.
It truly is. The research spearhead agent operates as the visionary R&D core for the whole platform. Its mission: to synthesize novel techniques and abstractions that might not even exist yet in current engine paradigms. It actively fuses developments across disparate scientific and technical disciplines, drawing insights from quantum computing research, advanced procedural math, novel rendering algorithms, and it proposes entirely new engine subsystems, innovative execution models, groundbreaking architectural theories. Its ultimate aim is to push the fundamental boundaries of real-time interactive technology by formalizing these bold new ideas into structured spearhead proposal.yaml formats. This seeds experimental paths for future implementation within the MCP framework. These agents together form this dynamic, intelligent ecosystem that continuously improves, maintains, and innovates the whole engine framework, all powered by MCP.
Wow. Okay, this deep dive has really shown us an incredibly sophisticated, potentially revolutionary system. As we wrap up, let's just zoom out for a second. Remind our listener of those foundational principles that MCP makes possible, the pillars that really tie all these powerful capabilities together.
Absolutely. Grasping these core tenets is key to seeing the full picture. First and foremost, MCP enables a truly declarative approach. You define your intent creative, technical, not the step-by-step how. This fundamentally changes how you interact with engine design, lets you focus on what you want, not get lost in the implementation weeds, puts creative vision first. Second, the whole system is inherently modular and extensible. All engine systems are pluggable, replaceable, easily extended with custom MCPs. This is incredibly powerful. It allows for domain-specific engine extensions. Imagine tailoring your engine precisely for specialized uses, medical sim, military training, scientific viz, virtual production, without the insane cost of forking a monolith or building from scratch. Third, and so important for quality and trust, it's deterministic. Every single build from the MCP pipeline is guaranteed reproducible. That's a game changer for QA, for debugging those tricky issues, for auditability, especially in regulated fields. You can trust that the engine you built today is the exact same tomorrow. And fourth, it's intrinsically AI operable. Every component, every process exposes rich metadata that AI agents can reason over. AI becomes a true co-creator, optimizer, maintainer. Intelligence baked into every layer, and finally, it offers profound cross-domain compatibility. This isn't just for games. It's designed as a universal rendering and simulation backbone for a huge range of industries. Immersive virtual production, precise digital twins, life-saving medical imaging, defense-grade sims. MCP provides a flexible, robust, powerful foundation for basically any real-time interactive application.
One of the most compelling threads throughout this has been this idea of developer agency. What does that really mean in practice when you're working with a system like Cadence and MCP? How does it empower the individual creator or the team?
In practice, it means you regain full creative and technical agency over your entire tech stack. The days of wrestling those bloated monolithic engines, accepting their whole feature set whether you need it or not, or conforming your unique vision to pre-built systems with all their built-in limits. Those days are really behind you with this approach. With MCP, you get to generate a custom-fit engine with only the systems you absolutely need. Cuts out all the unnecessary overhead and complexity. Plus, you use intelligent AI agents to iterate rapidly on architecture, optimize performance in real time, dynamically evolve your engine over time as your project changes. The engine stops being this external rigid tool and becomes a responsive, living extension of your design process. A flexible partner that bends to your creative will, not the other way around. It fundamentally empowers you to focus on the vision.
And beyond the individual project, what about bigger studios? Or even highly regulated enterprise uses? How does MCP handle the complex needs of scalability, security, rigorous governance in those demanding environments?
For larger orgs, the benefits are just as profound, yeah. That clean control planet data plane split we talked about, it allows for elastic build and bake farms behind a single MCP tool surface. Your dev infrastructure can auto-scale effortlessly, spin up thousands of VMs for compiles or asset processing, then spin back down. Optimizes resource use massively. Plus, using content addressable resources leads to incredible cache hits across different branches, teams, even product lines. Huge efficiency gain. Saves vast amounts of time and compute by avoiding redundant work across the whole org. The system's also meticulously built for robust governance, safety, and enterprise readiness right from the start. Includes things like policy-bound prompts, ensuring AI generation follows company standards or legal rules, software bill of materials, SBOM generation, comprehensive vulnerability scans, mechanisms for signing and attestation via security server tools for top-notch security and auditing, and crucially, determinism SLAs, service level agreements, act as strict gates for releases. Guarantees quality and reliability at scale, which is non-negotiable for enterprise stuff.
So ultimately, what kind of measurable impact can this whole approach, powered by MCP, really have on the industry, on the entire landscape of real-time creation? What are the North Star KPIs, the key metrics we should look at?
Yeah, the KPIs really show a profound shift in efficiency and capability. Time to engine, getting a custom functional engine is dramatically cut, from hours down to minutes thanks to caching and parallel processing. Change risk is significantly lower because of those determinism checks and controlled rollouts, ensures stability. Infrastructure cost goes down thanks to cache reuse and elastic workers, better resource use. Team throughput goes up, driven by clear declarative specs and AI prompts speeding things up. Lets devs do more faster. And finally, a vibrant partner ecosystem is set to grow exponentially through the open MCP server and plugin marketplace. Fosters huge innovation and collaboration across the whole industry. Hashtag tag, 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 outro one.
Wow. What an incredible deep dive. We've really journeyed through the nuts and bolts of the Model Context Protocol. We've seen how this open standard, supercharged by all these intelligent AI agents, just completely transforms game engine development. It shifts it from being this rigid, monolithic, often frustrating thing into something dynamic, declarative, and incredibly adaptable. You get to define your engine, tailor it exactly to your needs, and even watch it intelligently evolve and optimize itself. It feels like it truly puts the power back in your hands.
It really does. It's a compelling vision where the engine and the experience aren't separate things anymore, but this one cohesive, composable, totally portable whole driven directly by your creative intent. This isn't just a small tweak. It feels like the foundational tech for the next generation of real-time creation, affecting all digital domains. It democratizes engine creation, makes bespoke tech accessible to everyone, and enables this massive AI-assisted creativity that was just unimaginable for most developers before.
So just imagine this for a second. If you could define any game engine system exactly how you wanted it, with a smart AI as your dedicated co-architect, your optimizer, what incredible, previously impossible experience would you build first? What new digital frontiers would you want to explore?
The possibilities really do feel limitless, don't they? Stretching what we've even thought was feasible. We've really only just scratched the surface today of how powerful this shift enabled by MCP truly is for the future of creation.
Until next time, keep exploring, keep learning, and keep diving deep.